Okay, hi everybody, welcome back to Drunk Physics. Sitting here with some Bud Ice and thinking about the age of the universe. The first question to ask in this is, why is the age of the universe so readily determined? Why do we have this simple evolution of things? Why does it start expanding even faster? There are a lot of cosmological questions that have to do with answering just answering the age of the universe. Because when you look back into space, you can see this WMAP image that we've gotten. It's pretty much your radio static and your TV static. It comes in at about in a similar type of wavelength. You have electromagnetic radiation, and it goes anywhere from the negative, 1/100 repeats per second to, I don't know, the quantum limit of repeats per second, where basically every wavelength is a quanta of space and time. That's your limit. Those are your limits. You're not really limited by much. Now the WMAP, it's a thing that went out there. It's a satellite. It went out into space, and it gave us a map of the matter structure of the universe behind us. And when I say behind us, I mean in front of us. And when I say behind us and or in front of us, I mean backwards in time. Because when you go out into space, even if you're right here, you're right in front of my face, you're looking at somebody, you're talking to them, you're seeing them in the past. Through the magic of recording, I've looked at the Hubble constant. Okay, the Hubble constant is what we use to determine the age of the universe. That's because you have the scaling between radial velocity and distance in kilometers per second per megaparsec since it was first determined. So this is what you're looking at here. This map here tells you the Hubble constant. This is kilometers per seconds per megaparsec. That means that for every megaparsec out into space, let's say this axis in here was this axis here, which is time on this axis. Let's say it was space, and this is how much it's receding. Okay, so then you'd have the reverse of this. So every you go out into space like this way, you go out, that goes out into space, then things are going away from you faster. There's only a few reasons this happens. Actually, I can only think of one reason off the top of my head that this sort of thing happens. It's called, it relates to the spring constant, the rubber band constant, Hooke's law. Work equals the integral of kx, where k is Hooke's constant. That's a spring constant. So the further you go out, the more tension you have in a spring. So something like that, but it's different. The farther you are away, the farther a point on a membrane that's stretching out at the same rate, you pull a rubber band so that your thumbs move away from each other at the same rate. If you're here at the beginning where your first thumb is, you're going to stay stationary because all the expansion is happening away from you. It's a pretty simple concept. Then you have other points that are towards your other thumb that's moving away. Those are going to be moving away faster and faster as you go out. You can do this at home. You can actually take a rubber band and you can draw points on it when it's stationary and unstretched, and you can hold it down with a thumbtack or with your thumb, or just as you like, and you can pull it out and you can actually measure how far apart the other dots are from each other, and they will have that linear ratio. You're going to be able to actually see that law working. So when this happens over time with the universe, which is an expanding membrane, and a membrane, remember, or a continuum is basically a ball of silly putty. You can stretch and you can do whatever you want to the silly putty, but it's all the same unit. It's all the same thing unless you divide it. And when you divide it, you have to have a singularity there where it just and snaps. Okay, so we're not thinking about those situations. We're thinking about an expanding continuum membrane. Space and time itself is one membrane, one continuum. We have to keep this in mind. So we can see, actually, let's take a step back. Look here, the Hubble constant has been converging on a range of values since the idea was first conceived that as you go further back into space, things move away faster. It used to be, they thought, wow, it was moving away at like 600 kilometers every megaparsec you go back per second. Remember that. It's a velocity. It's a recession velocity. It's how far away the thing is getting from you and how fast. So with that in mind, we can actually trace this backwards. We can trace it back to the point where if you are expanding at that same rate, you can also contract it all at that same rate until it's down on one point. So we use in physics the idea that physics is a universe contracted on one point. Pausing for a second here. Okay, unpaused. I'm using the magic of Google here to pause this video and then find pictures that are relevant to what I'm talking about. So you have a singularity. Well, boil it back to the point where I said that you stretch a membrane apart so that it becomes two nodes, and then in the middle it splits. So maybe the universe is like bubbles in that case. Who really knows why the universe started expanding? But the thing is, it's one thing. It keeps expanding out. Into what? Okay, we're getting into questions that are becoming increasingly more unanswerable. But the point is that it started getting bigger. It started coming out from a singularity. This is a picture of a black hole, and it falls into a singularity. But the thing is, it happened in reverse. Then you can start talking about white holes or whatever you like. But when it happened in reverse, you go all the way back down to the singularity, and then all of a sudden you're left with something. It's one little single point in space. Now, these are mathematical idealizations. I can't stress that point enough. When you use something like a singularity in mathematics, that's bad physics. Nothing is infinitely dense, infinitely magnetic, whatever properties you want to give it. There's no such thing as divisions by zero that make sense in physics. When you do physics like that, you're doing bad math. It's that simple. The thing is, physicists know it's bad math and knows that there's no such thing as a singularity. That's why when you have math that behaves this way, when you work like this, you know you're doing something that doesn't quite make sense, but you're reaching a point where you see something happening. Now, the fact of the matter is, there is a Doppler redshift in the universe, okay? And I'm going to pause for a second and figure out a picture I can use to do that. Okay, so this is a picture of the idea of waves redshifting. So Doppler redshift happens when things move away from us. So we're right here. We're in the center of this picture, and things that are getting closer to us will appear to be having a wavelength of light that's shorter, and things that are getting farther away from us, we're going to appear to be having a wavelength of light that's longer, also redder. Why does this happen? It's a Doppler law. It's just a law. It's a thing that happens in the universe. But when you have a galaxy that's this far away, all the way out here to the very edge of the universe, you're going to see it with like visible light spectrum drawn all the way back into the infrared. So far that you can't actually see it. It's literally radio waves. You could pick it up on your FM or AM transceivers. And this happens for a very specific reason. It's because that object is getting farther away from us. And just like when you're in a tunnel and you hear an ambulance coming towards you, it's blue shifting in a sense. It's acoustic radio frequency. And then as it moves away from you, that wave starts growing longer again. What it's doing is it's approaching its actual pitch as it reaches you, and then it's moving away from that as it moves away from you. And it decreases in pitch, which is the same thing as a redshift. With light red shifts. It goes from redder to bluer as it gets closer, and then from bluer to even bluer as it gets farther away. No, I said that wrong. As it gets closer, it gets bluer, and then your light wavelength gets longer. Okay. So when it gets longer, that means that you can actually measure how far away from you it is by how bright you think it should be. and how bright it actually appears to be, which when it's all the way out here at the edge of the universe, it's completely redshifted to the point where you can't get farther away and you can't redshift more. On a similar topic, going there, you can use that redshifting ratio, how much it's redshifting versus how far away it is. You can use that ratio to rewind time to see when everything was as close together as it could possibly be. Like, basically when everything was right on top of itself. So, I mean, there's been a lot of things that bother me personally with the idea of a Doppler redshift. And looking out in the universe, there are other reasons a Doppler redshift can happen. Like, say the universe is gaining weight. There's more mass being flowed into it, and that would make intervals in space-time shorter due to laws of physics. Or make intervals of space-time longer, actually. There's a lot going into this, is what I'm trying to say. This is a very deep question. The age of the universe is not easily determined, and why it's so easily determined now versus why it wasn't before is a mega step in physics. You go from physics of thinking that the universe is static in space and time and does the exact same thing all the time to coming back to you. Alright, pausing for a second, I'm going to come up with another thing that's right on topic with what I have to say. So this is one thing right here. The expanding universe is exactly what I was just saying. This is the current value of Hubble's constant, 71 kilometers per second per megaparsec. What does that mean in English? That means that if you go out if you go out 1 megaparsec, let's call this distance right here 1 megaparsec. It's not important to know what that distance is, but the idea is that if you go out into space, that things start moving away from you faster and faster the more you go out. So when you go out here, it's moving half as fast as if you went twice as far. Okay, simple stuff. It falls on a line. Thinking about it that way, the expanding universe comes out like this. Now, let's go to this. Where did I even put that? Okay, so this is what I'm trying to say. The farther you go out, the farther it seems to move away in 1 unit of time every second. This is how we determine the age of the universe. You go all the way out from here, you retract it back here so that the rubber band is fully, it's slack. You let all the slack into the rubber band again. So, that said, you have this linear relationship of recession velocity and distance away from where you're receding from. We are one observer in the universe. We are on one planet, which we can consider 1 unit of space. However you want to consider that. We're looking out into space at things that are getting farther away from us. Then we're left with one simple equation, Hubble's law and constant. V equals hd. H is the Hubble constant. That's what we just discussed. That's that 71 kilometers per second per megaparsec value. And then you multiply that by the distance away from your center point, say here on Earth, where you are right now looking out at the stars. Every megaparsec away you go, things are moving 71 kilometers per second faster. Every 1 megaparsec. This is also called h sub 0, and it's like the initial value, because astronomers are realizing more and more that Hubble's value is not the same everywhere in time. That's an important point as well, but what we can do is we can linearly retract this value down to 0 and determine the amount of time it took for something a certain distance away to be right on top of us. Okay, so that's the next point. Pausing again. This picture right here sums it all up faster than I could, and I only had to Google it. The age of the universe equals separation distance over recessional velocity. I just said that. The same as inverse h sub 0. So the age of the universe is 1 over h sub 0. So we already know what h sub 0 is. That's 72. Well, we said 71 before. It's kind of like in that middle area between 71 and 72. So we can associate that with a certain value and then just kind of approximate it. I meant to say approximate when I said associate, but h sub 0 equals 72 over 3.09 times 10 to the 19. Why do we get these numbers? 3.09, well, that's first converting distance into kilometers. Okay, so 3.09 times 10 to the 19. I have to think about this for a second. Hold on. Okay, I think I get it. What they did here with the 3.09 times 10 to the 19. Okay, I think that is parsecs into it's megaparsecs into units of space, I think is what just happened here. It's not important to know exactly how this is working as it is to know that it works when you plug it in. When you use the units and when you do all of that, you kind of come up on a certain point where this just makes sense. This number right here is perfectly valid. H0 equals 72 over 3.1. Okay, so it's 72, we'll say, for this particular one. Why is it not 71? Well, that's not as important. It's called error in measurement. Everybody gets a slightly different value. Now we have 2.33 times 10 to the negative 18 seconds to the negative 1. Well, that's per second. Seconds to the negative 1 in physics is per second. So it moves 2.33 times 10 to the negative 18 meters per second away from us. Okay. So then we invert this value yet again, and you get 1 over h0. Which means that the universe has been doing this for 4.29 times 10 to the 17 seconds. Convert the amount of seconds that we just mentioned there into years, and then you get this value, 1.36 times 10 to the 10. 10 to the 10 is the tens of billions. 10 to the 9 is 1 single billion. 1 times 10 to the 9th power is 1 billion. So basically that means you move this right here, and then call this the unit. You move the decimal point from the 1 to behind the 3, and then call that unit tens of billions of years. That's how exponential numbers work. So we have 13.6 times 10 to the 10 billion years. Our current value is 13.82 billion years. I was almost certain that was what it was, but I had to look it up again. But here we give a little bit more information. So 13.73 plus or minus 0.012. That's an important point to make right there, that plus or minus. That plus or minus right here tells you that we are doing science. This uncertainty, this plus or minus, it means that we could be off. We scientists, I'm going to classify myself as a scientist because, you know, science. I like to do science. I like to do science. And if you like to do science, you're a scientist. And I'm going to classify myself among them. This 0.12 value means that this is how much we could be wrong. This is how much we know we could be off. Not really much out there. But then we had another spacecraft here, this Planck. This Planck spacecraft was another one that comes out that says, we were off. But within the range of error, we knew we were off. 13.73 plus or minus 0.012. So we have 8.2. So we were off by a factor of 0.11. The Planck got us just a little older than we thought it was, and that makes sense. Why does it make sense that the universe is older than WMAP determined? Well, it's been expanding. It's been expanding, but not only that, it's been expanding faster and faster for a certain epoch of time. That means that the redshift of light is getting even more redshift as it goes along, and you have to kind of rewind that and make it so that it becomes a one-to-one correspondence with the growth. So normally it would go on a line that goes, you know, straight. But then it starts curving and getting exponentially faster and faster. We have to account for that recent epoch of time. Really simple to think about, but really difficult to calculate. How do we calculate that? Pausing again, let's go and find something that relates. All right, let's dive into some math. This statement right here, I'm going to explain what this means in somewhat simple terms. H squared equals a dot over a squared. A dot means it's the first derivative. That dot over the a means it's a derivative. So the derivative over the original function squared equals this nonsense here. It's not nonsense. It's actually the exact opposite of nonsense. This actually allows you to calculate what's going on with the universe, how much energy it has, so forth and so on. The energy of the universe drives its expansion. Now, energy is related to mass. We know this. This is delving way down deep into the rabbit hole, but if you're still here with me, you deserve to be, because you can actually follow everything I'm saying. That means you probably have some background in physics and you're ready for this. K represents the total curvature of the universe. Okay, that's not an important thing to think about. Curvature differs with how big it is. A bigger bubble has less curvature than a smaller bubble, whereas a single point in space has infinite curvature. Okay, so we define a critical density. Rho actually sub c equals 3h squared over 8 pi g. And the density parameter omega, which is not actually in this equation, is rho over rho c. So then, using this identity here, we can actually talk about the Hubble parameter as this. So this whole equation right here is a Hubble parameter. When we say the Hubble constant, that's wrong. The Hubble constant is not a constant. It changes in time and in space based off of a lot of things that are going on with space and time and its expansion. Okay? Cosmic speed up happens when the universe gains weight. It starts contracting into denser and denser bits of matter instead of being uniformly distributed out throughout space. So that causes things to want to move away from each other or something. There's something going on here. Dark energy, dark matter. That is a topic for the next one. And at the behest of a friend of mine, I'm going to start doing more and more information, observation, everything, so forth, into what this actually means. For now, we're left with this idea that everything that expands in space and time does so according to rules of physics. And I'm sorry this is so low budget and so I'm using Google to find everything, but this is all real stuff. I've read this in books. I know this is physics and I know why it's physics, and I think that's the most important point. Hold on, we're going to pause for a second and look up something else. I paused too soon. Okay. So we've already arrived at the edge of the universe. The age of the universe is the edge of the universe. That's as far back in time as we can see, and when you rewind how far back that is, you do some work on mathematics in its Doppler redshift as it's gotten to you, you realize that something's happened. The universe has been expanding, but it's also been expanding faster and faster as time's been reaching us. Well, that actually kind of means the opposite when you look at it from the point of view of the thing that's expanding away from you. That means that actually it's been expanding slower and slower as it gets to us. It's the opposite. That doesn't really make a lot of sense right now, but if you think about it along these terms, it'll make a little more sense. Okay, first of all, when you come back from us, it's expanding faster and faster now. But it wasn't before, which means that this rate we've been seeing it expand is only just starting to show itself. So it's just starting to grow. So for the better or worse of space and time and everything we've learned about it through the Einstein field equations and everything now, we can come up on this thing called the Friedmann equations. We assume, first of all, that space is homogeneous and isotropic. That means that in this little picture here, you're seeing basically the same within a little bit of fluctuation. It's pretty much the same picture. All of the points here where they're redder are going to even out with the ones that are very blue. So this big patch right here evens out with this big patch of red and yellow and green right here. So it's all, for the most part, pretty much the same density, the same mass, the same density. That's isometric, isotropic. It's the same everywhere, and it's pretty much the same meter, the same metric. Now, this is obviously a lot of mathematical idealization, but it works, and it works for a few reasons. Hold on for a second, I need to reflect. Okay, so I've read this. The cosmological principle implies that the metric of the universe must be of the form ds squared equals at squared ds3 ds squared ds3 ds sub 3 squared minus ct dt squared. Hard to say out loud, but when I'm reading it in my head, it makes perfect sense.
Yes.
Okay, I just got distracted for a little while, but I forgot almost completely where I was. But I also know that I'm talking about this idea here, the scale factor. This is this at squared. This is what I was talking about when I said that the Hubble constant is more like a parameter. It changes in time. So this at, it means it's a function of time that changes this ds2 or this ds3. It changes like one axis of time. Okay, this ds sub 3. The other two axes remain the same. And then it also changes c squared dt squared. It changes time with the usual, negative signature. If you know what that means, then you know a lot more physics than a lot of people pretend to. There's a lot more to the picture. There's a lot more to discuss here, but this is a really somewhat rigorous overview. I'm basically showing you the equations that we use in physics and explaining why they work, not what they are or how they work. I have a couple minutes left before my 30-minute mark here, which is where I try to end my videos. This right here, this is mostly meaningless to anybody who doesn't know physics. What it really says is that when you have a universe that is expanding, there's some way to kind of rewind it back to how long it's been expanding. And a universe that is expanding at the same rate has to have been expanding for one amount of time. Only one. There's one solution to this equation. You can't have many ages of the universe unless you have many parameters. So what we're trying to do is we're trying to get this parameter down to something that makes sense in terms of modern physics. And the more you try to think about what that parameter is and what its value is, the more you start to align it to that somewhere in the early 70s. 71 kilometers per megaparsec. Kilometers per second per megaparsec. 72 kilometers per second per megaparsec. 73, 4, 5, however you like. It can be 300. We can talk about a universe that expands at that rate, which is, I don't know, like 35 times faster than it's doing right now. Which is probably about what it's doing right now. It's probably expanding about 35 times faster than it was before. The point is, everything expands. And we can know how long it's been expanding just by how expanded it is. And how fast it's been expanding. And this has been the second episode of Drunk Physics. I hope you've enjoyed this talk as much as I've enjoyed talking about it. And if you like it, there will be much more to come. And if you like what you hear, support me on Patreon. Please do. I have one Patreon for all my accounts, but I do lots and lots of different things. So, I mean, if you want me to keep churning out content, pay me. I like to know that I'm being supported for what I do. So, without further ado, this has been Drunk Physics. Everybody take care. Have a magnificent time and stay out of the way of hurricanes, because that's been a thing lately.